So there's the scope, Tektronix 2236, 80s model, and it still works pretty well. It triggers reliably. It probably is out of calibration, but it suits my needs for now just fine. And one interesting thing about it is this little vacuum fluorescent display here, which is actually on right now, but it's so dim you can't even see it anymore. I'll turn this light out. Right. It actually works better on camera than it does in real life, because I can't, with the naked eye, I can't read that. Maybe if this fix doesn't work, I'll set this camera up in front of it so I can read it. But that's what it does. Frequency counter, voltmeter, has an ohm meter. It does a lot of stuff. It has these inputs. Let me get around there. This extra set of inputs on the side here for dedicated probes for reading resistance and voltage, but this is in its frequency counter mode. It has these other feature buttons right here to control what this little display does, but the display is so dim that I cannot read it anymore, and I'm it's funny that it works much better on camera than it does to the naked eye. But let's take it apart and see if we can see if we see anything wrong, or if the display is just aging and needs a little boost, and we'll give it a try. Alright, so this is the first time I've had this thing apart. I got it at a ham fest earlier this year, and it's done its job. I knew about the dim fluorescent display at that time and wasn't too worried about it, but you know, Todd had to go and fix his car radio, so now I have to do something about this. So let's take a look around. We've got let's see, danger, these screws and all components inside are at multimeter input potential. Use only insulated tool when making adjustments. Fine. It's not what we're here for. There's a rod mounted pot there, the time position, delta time position pot. Runs all the way back to this board, and that board has a lot of discrete goodies on it. Lots and lots of chips. What is the date on this thing? This isn't a manual. I know it's an 80s vintage, but I don't know from what era. Let's see. Date codes. Date codes 83, 84, 85. Okay. Yeah, 84, 85. There are some 85 chips in there. So mid 80s somewhere. Something under this shield there. I think that's the neighborhood I want to be in. These big connectors here look like they're wired up to that display. Under that shield, of course, there's nothing. I guess I gotta get into that shield to find what I'm after. Being mindful of the CRT high voltage potential that's in there. Let's take a look around at this thing first. There's the multimeter inputs, and I guess all the multimeter stuff is in this box to keep it isolated. A lot of interesting looking boards and things in there. Do not remove this shield while line cord is connected. Very well. Danger, 100 volts DC present on this area of board. I really like these old boards with all the silk screen. Everything's silk screened on the bottom, so you can find everything from the bottom side. Don't have to go taking it completely apart to check your test points. There's a CRT. That delay line in the bottom, and the CRT is taking up a whole rest of that on the inside. So got a, oh, what's this? There's another big board on the bottom that drives that CRT yoke. And some big, there we go, big resistors and lots of analog goodness down there, all discrete stuff. Adjustments that we won't be messing with today. Alright, let's get into that and see what we can find out about this display. It sort of looks like it's on its own board there, apart from everything else. Let's see if we can get that out of there. Worthy of note here is that this board is loose in here. So I'm not the first one to go poking around in here. Maybe the ham that sold this to me at the Ham Fest knew a little more about it than what he had told me. Well, used gear. Buyer beware. Let's take it apart. There it is without the covers on the multimeter parts. Right, and there's the these two driver. I'm gonna grab something to point with. These two chips here, 6118P, are the drivers for that display. And all I've done so far is take it apart, get these covers off, unplug these little connectors and plug them back in, and powered it up. And this is what I got now. This is interesting. Blinking fail-D. And everything still works. I've still got a trace on it. Maybe there's an interlock on that cover or something, so it doesn't operate the. Yeah, I don't know. Anyhow, let's check some voltages on that on these connectors. Make sure we have schematic says 30 volts into those driver chips, and so on. Let's check a few things. Hey there, it's a new day. Taking another crack at this thing, and that waveform on there is of interest. That is the filament voltage. Let me show you I gotta hold up a schematic for this thing that makes this a lot easier. Let me wheel you around to the computer here. Okay. There's my display. And there, that F2 is clearly the filament wires there, and terminates in F1 on this side, driven by this little circuit here with a JK flip-flop there. You see both J and K are wired high, and the clock is strobed from another chip down here. But with that JK flip-flop wired that way, it should just toggle. It should just be a T flip-flop. It should just toggle that Q pin on pin 1 on and off with every pulse of the clock. So it goes through all of the transistor stuff there, and eventually hits those pins on the display, and I've got those hooked up here. For some reason that's what they look like, which in and of itself isn't a problem, except the manual shows those waveforms. The bottom one there shows it at a, well, now it's a drawing, but it shows it at a 50% duty cycle. 4.2 volts at the top, about 1.5 at the bottom, and we don't have that. We've got this about 1 volt above ground, and about 3.5 volts at the high point, and so each of these channels is hooked up to one end of that filament, and they're exactly out of phase with each other. So the timing is a little weird. So I don't quite get that, and I'll show you what else is strange. Hang on, let me reset here, reset that channel B on another pin. Let me show you what else is interesting. Okay, so that JK flip-flop up there, I'll show you the output of it. This is pin 1, the Q pin of that flip-flop, and it's exactly what the output of the transistor amp is, going into one end of that filament, and of course the other end gets the exact inverted signal. So the output of the transistors agrees exactly with the output of that flip-flop, but look at the clock pulse of that flip-flop. Now that's just weird. That rising edge of the clock, the clock pulse is the bottom one. The output of the flip-flop is the top waveform. The rising edge of the clock pulse on the bottom waveform comes in and should toggle that output from whatever it is to whatever it needs to be. So that lines up where that top waveform goes from low to high right there. That makes sense, but what is going on there? Sorry, I've got both hands in use right now. Let me try this. Right here, why does that output fall off there when there's no clock pulse telling it to toggle right there? And for that matter, why does it toggle up again? Let me slow my time base down. Now you can really see where those clock pulses are falling and how much activity there is in between them that shouldn't be there. That's pretty strange. Okay, I brought in another scope, not because I needed to. I was able to see these same waveforms on that scope there. Even I'm able to work on it with itself. Anyway, I got another scope in here, and I want to show you what's going on. This what we're looking at is that chip right there, that 4027B. The top one is what's actually making it all the way into the filament of the fluorescent tube. The middle one down is the output of that flip-flop, And this, let me get a probe on here with my other hand. Hang on, this is there. That is the output of the clock, or excuse me, the input clock pulse going in on pin 3 of that flip-flop. So with every rising pulse, with every rising edge of that pulse right there, it should switch states. So there, those line up with that pulse, and you can see the trailing edge in the corner of that other one, and it rises. But what is all that in between? There in the left side, it comes off a rising edge, and they're both high. The other two channels are both high, and then they just fall low, and then go back high, and then drop low again, and then they get the next clock pulse and go high again, and start the same thing over again. What the hell is all that? That's not what that chip is supposed to be doing. Maybe that chip is bad. I'm gonna see if I can get another one of those and swap it out. Or maybe I can simulate a JK flip-flop in software with one of these little dev boards, intercept that clock pulse, and just toggle a couple of output pins, inject that into my circuit here, and see what it does. That'd be kind of interesting. That'd be fun to try. Alright, so let's see what we can do. So let me tell you why I'm looking at that chip, well, the waveforms coming out of that chip, with suspicion. This is what a JK flip-flop is. CD4027 is what we're looking at. In this gear, there are other versions of it, but they all work kind of the same way. J and K are inputs. S and R is for set and reset. It puts it into a known state. The clock is just your data clock, just clock pulses coming in. Q is the output. Not Q is an inverse of the output. So whatever Q is, this will be the inverse of it. And here's a truth table of the way it works. It changes state with every rising clock pulse that comes in on that clock pin here. Every rising edge of a clock pulse, every one of these that comes in, changes the output based on what these inputs are set to. Zeros, ones, the X's means it doesn't care what that one is set to. So in the first line, if J is set low, we don't care what K is. If S and R are 0, 0. If the output is presently 0, if Q is presently 0, the inputs are set this way. When that clock pulse comes in, we're going to change the outputs 0, 1. So no change on the outputs in this case. If the output is presently set to 1, and we don't care what J is because K is set to 1, set and reset are still low, we're going to change the output to 0 and inverse to 1. So an output change, if K is set to 1, set and reset are 0, and the output is presently 1. Remember that, that's important. If the output is presently 0, we have a 1 on the J input. We don't care what K is, these are 0. There's a state change there from 0 to 1 that follows J, okay? And if the output is 1, we can ignore J. If the rest of them are 0, this is the output we get. No state change there either. Okay, so these two are important, right? These, if you have J and K set to 1. With each clock pulse, it flips the state of the output from what it presently was. If it's this, the clock comes in, the outputs are set this way, it's going to invert the outputs. So that means if we have that device wired up this way, as in our oscilloscope, where J and K are tied high, set and reset are tied to ground, with every clock pulse that comes in, with every clock pulse that comes in to this clock pin here, this is the output we're going to get. It's going to go high, which will drive this one low. Then the next pulse, the next clock pulse, will send this one low and that one high. The next clock pulse comes in, it goes back high, this one goes back low. So it just toggles. It just toggles these outputs, and these don't ever change. So with every clock pulse, the output toggles. That's just one way of using this JK flip-flop based on these two these two items in the truth table here. So there's nothing else wired to that chip. That's really the way it is in the schematic, so there's really no reason for it to be toggling out of sync with the clock like it is. You saw the waveform on the scope, and it's just kind of all over the place. It's not toggling. Excuse me. It's not toggling solely on the rising edge of the clock coming in. It's just kind of doing whatever it wants, and some of the state changes do coincide with the rising edge of the clock, but it has a lot of stuff in between each clock pulse that doesn't make a lot of sense. So my gut tells me to replace that chip. I don't have one to replace it, but here's what I've got instead. The TI MSP 430 launch pad. It's about $5. Just a microcontroller. It can't be that hard to emulate that behavior in software. Just dedicate a few pins, accept a clock pulse in on one of the pins, and flop the outputs with each incoming clock pulse. It should be pretty easy to do, and that's what I'm thinking I'd like to try. I'll just emulate a JK flip-flop in software and wire, since the device in the circuit over there has a clock coming in, I'll just take that clock signal, send it into a pin on the micro here, and then take the outputs. When it toggles its output pins, I'll just take that output and inject it back into the circuit where this one would be, so it behaves the way this truth table suggests it should. I don't know if it's going to work. Let's try it. And here, I mean, that right there, that's all the code it takes for this behavior, so I'll kind of walk through it. Just let's start at the top. We'll define which pins we want to use. I'm going to call that one clock in for pin, for port 1, pin 1.1, right? That's the way they do it. Port 1, pin 1.3 is our Q output, and not Q will be port 1, pin 1.5. Alright, so there's our main method. We're just going to turn off the watchdog timer, pick a clock frequency. The super low energy saving frequency is fine. We're not going to do a whole lot. It just doesn't need to be really fast. This thing's running about 133 hertz, 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 set our clock in and able to pull up resistor on it. Set the direction for Q and not Q to be outputs, and the clock in to be an input. P1 out equals, and then we're just setting the initial state of the input and outputs. Then we enable the interrupt for clock in, the clock in pin, and tell it the P1 IES, we're telling it to look for the rising edge of a change on that pin. Then we clear the interrupt flag and we put it to sleep. Then this is our interrupt service routine here. When a change occurs on our clock pin, it's going to trigger this function here as our interrupt service routine, and all we do is toggle Q and not Q from whatever they were to the next state, so they're just flip-flop back and forth. And then we clear the interrupt flag. That is it. That is going to do what that chip is supposed to be doing. So let's put it on the scope, make sure it works, see if we can wire it in. What I've done is tap into pin 3, the clock pin of that JK flip-flop chip with just a small signal diode, the anode of which is attached to this red wire, and carries the clock signal over to this little MSP430 board. I have a bunch of these laying around. They're $5. If I blow it up, it doesn't really matter that much. Anyway, I've got a little program in it and a couple of pins hooked up there. So now let me get on. Turn this light off so you can see. Alright. That signal at the bottom, that bottom trace, alright, you can see there's two little pulses there. That's the clock coming in from the other scope, level shifted down to 3.3 volts to go into the launch pad, or the MSP430 rather. The two signals above it, channel 1 and channel 2 up above, are what I'm going to call Q and not Q, what would be the outputs of the flip-flop. So you can see at the rising edge of that clock pulse, these things just toggle back and forth, and with each clock pulse they'll switch states. Q and not Q will just reverse each other. And that is what that chip is supposed to do. These are just output buffers, current amplifiers that drive the filament of this display. So if I can drive those transistors, even though my output is on 3.3 volts, my output from my launch pad is at 3.3 volts, but if I can drive those transistors with that and get different results on the front panel here, I think we can call that a bad chip and just replace it. This is a 4027, it's pretty common, but this is kind of a fun way of determining that without swapping out parts. Okay, here we go. I wanted to bring you with me. There is my four resistors. The base resistors for those four transistors lifted out of circuit and away from that believed to be defective chip. There is the level shifting diode. There's my clock on the red. and the white and black are going to inject my Q, not Q signals from the MSP430, and I've got those two on the scope there. So all that's left to do is turn this sucker on. It should generate a clock pulse, and we should start to get waveforms over there, and hopefully get a display over here. Alright, here we go. Alright, there's my waveforms I wanted to see. A little jittery. And there's, well, pretty much the same dim display as I had before. So that's kind of lame. I don't know, maybe it's a little brighter. But scope my clock pulse. Well, I know I've got a clock pulse because I've got things toggling around up there. Alright, there's my clock pulse at the bottom from the other machine, and my toggled pins there. And we've got, the display is still kind of dim, but I feel like it's better than it was before. So, not sure what to think about that other than, well, other than this crazy Wile E. Coyote setup works, because I've got a display at all. If you run it without those resistors in circuit, by the way, you get a completely black display. It doesn't light up at all, which is what you'd expect. So I wouldn't call that success because the display is still pretty dim. Could just be the display itself, I suppose. Just want to show you one other thing here. That, alright, the top waveform is my injected signal from the microcontroller simulating the flip-flop. The second waveform down is the clock signal from the scope that I'm using to trigger my flip-flop, and the bottom waveform is the output of that 4027 that should look like the top waveform. And you can see all that trash to the left. I don't know why it's doing that. Right here on the rising edge to the right, that's okay, but then it cuts off and does all this goofy stuff in the middle. Anyway, let's replace that chip and see what we get out of it. Alright, one more thing I'm going to try. This red lead here, that's new. That is on another lifted resistor, and it is the resistor that brings in the 5-volt supply to this this little transistor bunch here that drive the filaments from this waveform I'm generating with the MSP430. It's still doing its job over there, so now I've got that resistor lifted out, it's completely dark. The display is completely dark, as you'd expect. So now I'm going to start bringing that up on a variable power supply and see. I'm just going to watch what happens here at 1.5 volts, 2.5, 2.7, 3 volts. Okay, I can see a little faint glow there. 4.3, 4.5. Yeah, 5 volts. Okay, that's where it lives normally. And it looks pretty good on camera, pretty dim to the naked eye. So I'm going to bring it up to 6 volts. And that doesn't look too bad. I can take it back down to 5. Yeah, down at 5 it gets pretty dim. Six volts, it's starting to look pretty good. Could be brighter. We're already here, right? Might as well take it up a little more. 6.25. Six and a half. It's starting to dim on me again. Oop. Yeah, at 6.5, it just goes dim. That's weird. Okay, the sweet spot seems to be at 6 volts to brighten that thing up. It starts to go dim above that. Well, I can live with that, I think. Again, it doesn't look that good to the naked eye. Looks pretty good on camera, but alright, I'll just find a way to inject 6 volts at that 5 volt input. Give it a new whoa, shoddy camera work, sorry. I think I'll replace that chip just on general principle. Put the whole thing back together and see what we got. Another update. I found that when I soldered these resistors back in and left the original IC in, it's still there. But I soldered these resistors back in and played around with my variable power supply a little more on that resistor that's loose right there, and found that in its original configuration, without my injecting the 3.3 volt software flip-flop, let's call it, this thing driving at 5 volts like it's supposed to, or at least as best it can, with 7 volts injected on that resistor right there, makes the display acceptably viewable. So it's driven by 5 volts. The 5 volt supply is fine, but that fluorescent display wants 7 volts now in its advanced age. So I was looking at the schematic, and I saw that the power supply for this thing has an 8.6 volt line that runs a few different things, plus and minus 8.6 volts, and I found that it comes up from the power supply through the main board, through this harness, through that harness, and right there you can see it says 8.6 volts. That top resistor there 8.6. The one below it is minus 8.6, so I gotta not screw that up, but I can tap into there and run a bodge wire over to there, oops, to there, and just run a bodge wire through from there through, I'm thinking 3 diodes in series to knock that down, that 8.6 volts down to as near to 7 volts as I'm going to get without doing something a little more extravagant, and I think I'll call it a day after that if that works. I did meter the current consumption of the filament of that display, and it only draws 15 milliamps at 7 volts. So there's probably no reason why I can't get away with that. So I'm gonna solder these diodes together right quick. I'm just gonna do a quick, just stick these guys together in series and stick them on here and see what I get. Yep, that'll do. I'm getting I just got it hot wired in here with 2 diodes. I get 6.8 volts. 3 knocked it down a little too much, so I'll go with 2 in series off that 8.6 volt point right there. And just lay on the table there and into that resistor. So 2 diodes, 6.8 volts gives me my display back. I don't know how long it'll last like that, but it's next to useless now, so I haven't lost that much if I burn it up. Let's put it together. And there it is, that white wire. Just tapped in straight to the output side of that resistor, and I'll get some hot glue in there to stick that wire down. Got heat shrink and just into that resistor there, and here's my display. Much more usable. I know it still looks better on camera than in person, but I can actually read that now. So there you go. Hope you enjoyed that. I still may replace that flip-flop after all, just to satisfy curiosity, because I still don't think it's exactly doing what it's supposed to do. That 4027 there, but another update maybe. Thanks for watching.